Okay, so yesterday we analyzed one part of this spring system for its gravitational potential, its kinetic, and its elastic potential energy. I left the results from yesterday's work down here at the bottom in pink, as well as the mechanical energy that we got up here, also in pink, of 1.82 joules. Today our goal is to do the same kind of analysis for the top part of this oscillation, and I'm going to play this for a second just so that we can see sort of what I mean. So right now, we're really focusing on this top part of that period trace. And if I want to analyze that, I'm going to go ahead and click this slow button because my goal is to pause this simulation right when that mass is at the top point of this oscillation. And right now I paused it a little too early. There we go. So really the way that you can tell that it's at the top of that oscillation is this period trace will go flat for a second, saying that this has momentarily stopped before it goes back down. And then at the bottom of that period trace, at this lowest point that we analyzed yesterday, there would be another flat line at the bottom here. But with this slow setting activated, I was able to pause this at the top part of that oscillation, and we'll move from there. So I'm going to erase those results from yesterday except for our mechanical energy, just to make room for our work for today. And we're using all the same equations as yesterday, all the same ideas, only a few things are going to be changing. So if we're going to calculate this elastic potential energy first, we need to use our hopefully now familiar elastic potential energy equation, 1/2 kx squared. The K for this spring, for the 5-notch spring, is 7.84. For the 3-notch spring that you all are using, it's just over 6.1 newtons per meter. I think it's 6.125. And so I'm just going to plug right into here. Now, as a reminder, for this x in that equation, for our displacement, we need to basically measure this green vector that shows our displacement. It looks like from the top here at 0 down to this mass equilibrium that is 23 centimeters. So at that green point at the very top, that is about 23 centimeters. And to convert that to meters, I know I need to move the decimal twice to the left or divide by 100, and I would get 0.23 meters. And so that's what I'm going to plug in to this equation. So our elastic potential energy here then is 1/2 times 7.84 times 0.23 squared. That is supposed to be a 3, although clearly I'm having trouble writing that. But if you plug this into your calculator, I would say the most important thing not to forget is that squared. So I'm going to do 0.5 times 7.84 times 0.23 times 0.23. And my calculator is giving me about 0.21 joules of elastic potential energy at this highest point in our oscillation. And to calculate these other energies, again, we're going to follow a very similar procedure for what we did yesterday. Only difference here is that it looks like at this point the height that I have, and let me rewrite our equation for that gravitational potential energy. So our gravitational potential energy is still mgh, mass times gravity times height. And if I want to figure out what that number is, I'm going to need to measure the height, even though I know gravity is 9.8 meters per second squared on Earth, and it tells us that in the simulation. Our mass is whatever we set it to, so for you all that'll be 100 grams or 0.1 kilograms. For me it is 150 grams or 0.15 kilograms, and I just need to measure this height. And as a reminder, we measure that height as the distance from the ground down here where it says height equals 0 up to the center of mass for this object that's on the spring. So I'm going to go ahead and I'm going to put the sort of 0 part of this meter stick right in the middle, or approximately in the middle of this mass. And then I'm going to move this sort of movable line right to the bottom there. And the way that you all have done this before in class, is like when you were measuring distances over a meter, you would sort of use a meter stick, mark it off like maybe with your finger or with one of your like lab mates' feet, and then just like move the meter stick to the beginning of where their foot was or where your finger was. So we have 1 full meter here, and we just need to figure out what this missing distance is there. So 1 meter plus an additional, and then to go from the bottom here up to about 88 centimeters. It looks like that height, let me write this over here, at this highest point is the 1 full meter point, and then our decimal just basically becomes however many centimeters we have here. So 1.111 meters, or 1.11 meters. It looks like it gets to about 11 centimeters from the ground up to this, like where the meter stick ended previously. So now let's go ahead and calculate that. So the mass of this is 0.15 kilograms. The gravity is 9.8 meters per second squared, and then the height we plug in is 1.1 meters. And so now, since those are all just right next to each other, we multiply those together, and what we get is 1.6317, and I'm just going to write 1.63 joules. Again, joules, because this is an energy that we were calculating, and joules are always our units for energy. And if you ever need to check, is your answer a reasonable one? It looks to me, based on these numbers, like our gravitational potential energy is a lot higher than our elastic potential energy. If I had to guess, it looks like our gravitational potential is like a little less than 8 times as big as our elastic potential energy. And then if we come over to this simulation, it does look like this dark blue bar, our gravitational potential is a lot less, or a lot greater than this elastic potential energy. So that makes me think that our numbers should be just about right. Now, for the kinetic energy, again, sort of like how we analyzed what the kinetic energy was at this sort of bottom point, we can look at this energy graph. It looks like this kinetic energy is basically just about 0. And so I'm actually going to write that here. Our energy graph shows in this bar graph that there is really no kinetic energy. There's almost no green bar here. The other way to think about this is, throughout the year we've talked about what happens when an object gets to the very top of its trajectory, like when you toss a ball or anything up into the air. At the very peak of its trajectory, it stops momentarily, and then it comes back down to the ground, and then it'll come back up, and it'll keep doing that. So we know at the very top of an object's trajectory, it really shouldn't have any velocity, it shouldn't have any kinetic energy. And we actually did that with roller coasters too. So at this top point, your kinetic energy really should be 0. And what that does for us is that when we calculate that mechanical energy, which again is just the sum of all 3 of these types of energy, 1.63 plus 0.21, so that's our gravitational potential, plus our elastic potential energy, 0.21, it looks like we get 1.84 joules at that second point, or at that highest point in the oscillation, which is pretty close to the mechanical energy that we got in the sort of lowest bottom point. I'm leaving it up to you to sort of try to explain why that discrepancy might be there, but that's definitely something to think about. But overall, very similar process to what we did in yesterday's